Okay, this is your Chapter 9 video, and the title of this chapter is Property of Gases. So the entire chapter is about gases, and I actually think that I find that students um, feel pretty comfortable with this chapter. It's not difficult conceptually. So here's what we're going to cover. We're going to introduce some properties of gases. We'll talk about effusion and diffusion, distinguish between those, talk about kinetic and molecular theory, atmospheric pressure, and then I'll excuse me, talk about the gas laws. And there's obviously quite a few gas laws, so that'll be a big chunk of the video. We'll go through introducing these and go into much more detail in lecture. So when we think about gases, we think about the different properties of gases. And you might think about, if you've got a particular cylinder of gas, and you've got gases in there, what's going on with those gases depends on several things. The number of gas molecules, right? In chemistry, of course, that's moles. So the number of particles, we know that moles are related to numbers of particles through our Avogadro's number. So the number of gas particles, now they could be atoms or they could be molecules. It could be like argon, which would be single atoms. They could be diatoms like hydrogen gas, or they could be things like carbon dioxide molecules. But the number of moles that are there. The pressure, we use N for moles and P for pressure. The volume that's there, right? The temperature of that gas. And they're all related. And you know some of this stuff, of course. You know that, at higher temperature, pressures get higher. Tell you not to store like an aerosol can in your car in the summer because it could explode or rupture. When you check the pressure of your tires in your car, your bicycle, it's depending on, if the car is just driven and tires are hot and it's a hot summer day, then the pressure is going to be greater. So all these things are related. And we'll look at that relationship a little bit further on in the video. But these are some of the things that we think about when we think about gases. Another thing that's introduced in this chapter is the density of gases. And you all know what density is. It's mass per unit volume. So what kind of matter per given volume is there? So there's two concepts we want to talk about early on, and that is effusion and diffusion. We'll do this in context with kinetic molecular theory. And it's pretty simple to distinguish between these. Now, your book goes into a lot more mathematical details about effusion and diffusion and, root mean square and, average speeds and all of this. You're not responsible for any of that quantitatively. And there's some examples that are there that you're not responsible for. I'm going to think about this qualitatively. First of all, effusion compared to diffusion. Effusion is escaping through a hole, okay? Okay, so gases can actually escape through the material of a balloon because of imperfections in that material. Or if they're small enough and the holes are big enough that gases can go through. That would be effusion. Or through the nipple where the balloon is tied or something like that. That would be effusion. Gas is moving through a space into another space. Okay? And you could see here that the rate at which it moves is inversely proportional to the density. Now, it's actually the square root, but I don't care that we focus on that. I care that you recognize that the rate at which it moves is inversely related to its mass and its density. And that should make sense to you. The heavier the gas, the slower it moves. So if it was directly proportional, we'd say, okay, well, that means the heavier the gas, the faster it moves. And this is the same thing with, other objects, not just gases, of course. So that shouldn't be that much of a surprise to you. And since density is mass per unit volume, then obviously that relates to effusion. Now, with kinetic molecular theory, this is simply all of the theory describing how gases behave. Okay? And if you look at this, they have tiny volumes compared to the volume of gas that it occupies. That means we say that gases have very little interaction among each other. Okay? So they're very seldom, partnering up, if you will, like they do in solution or solids. They're independent. And they're moving along until they hit something, whether that be another gas molecule or the wall of the container that's holding them. Okay? And the space is huge compared to liquids and gases. Okay? So we say we really don't interact with each other. If they do collide, we say the collisions are elastic, which means they bounce off and they go in a new direction, but the energy is conserved, and that is one gas molecule might slow down from the collision, but the other one is going to speed up proportionally so that the energy is conserved. We think about kinetic energy. Remember what kinetic energy is. It's 1/2 the mass times the velocity squared. So basically, it's related to the speed of the gas molecule. And the last statement there, kinetic molecular theory, is that the kinetic energy of the gas molecules is proportional to the absolute temperature. Now, I mentioned temperature here. What I didn't say that in gases, temperature always, we have to use Kelvin for gas laws. Anytime you're given a problem, you better convert that temperature to Kelvin. You will not get the right answer. That'll become more clear in class. That's something I'm going to discuss in class and talk about Boyles Law in detail in class. Now, diffusion is the spreading out. Okay, so you can do this with non-gases, easier to visualize. If I take food coloring and drop it into a beaker of water, that food coloring spreads out. That's diffusion. Okay? It also works with gases too, spreading out and filling the space. Okay? That's diffusion. That's really all I'm going to say about diffusion. Okay. Now, atmospheric pressure. We all know there's an atmospheric pressure. You report this in the Weather Channel. You see it. People talk about it. We know how pressure decreases as you go up in altitude, right? You always hear things like, oh, yeah, Mile High Stadium in Denver, the air's thin there. Athletes that come and play there, they struggle compared to the athletes that train there. The air's thinner. It's tougher to breathe. So what happens is pressure is the force per unit area, and you have a force or a column of air sitting on top of you. That's the pressure you feel. So here's a barometer here, and what we see is atmospheric pressure pushing down on the mercury in this case, and this is an open system. Mercury barometer is not going to be structured like this, but this just shows it. This pushes the mercury up the column. This has to be a vacuum here so the mercury can rise and fall at will, and if this was filled with air, that would keep it from happening. So at normal sea level, we say this rises to 760 millimeters of mercury. That's the height it rises to. That's equivalent to 1 atmosphere when we look at pressure units. It's also equivalent to 760 torr. Those are different units. That's literally the height the mercury column rises, 760 millimeters. One reason we use mercury is because it's very dense. Okay, it won't rise very far. I can make a barometer out of water or other liquids, alcohol and things like this, but I'll need a room that's 30 feet tall, ceiling's 30 feet tall to fit the barometer in there, because that's how high it's going to rise. So that's one reason we use mercury. So if I take this up to Mile High Stadium now, you're higher up, so the column of air sitting on top of you of less, the pressure decreases, and I forget exactly what it is, but it's something like 0.83 atmospheres. So almost a 20% reduction in pressure. Well, breathing is the difference in pressure between what's in your lungs and the atmosphere. And the lower the atmospheric pressure, the less of a force pushing in the air to your lungs. So you kind of have to suck the air in more. That's kind of sucking air, right? Or sucking wind or something like that, right? You struggle to breathe, okay? So the lower the pressure, the more work your lungs have to do to get that air in, and that's the reason you see that. So this is how we measure atmospheric pressure, and this is what we think about as far as atmospheric pressure. Now, with the gas laws, what I want to do, this is not something no textbook ever does, but all gas laws, except for a couple of them, can be derived from the ideal gas law. But since the gas laws were developed, first with Boyles and then Charles by the scientists working with these, and that's the history of it. And the ideal gas law came later once we had delineated these relationships. No one ever teaches it like this. But it's so much easier to teach it like this when we look at this relationship here. We have PV equals nRT. How does this come about? Well, we think about pressure and volume. And we think about a cylinder. Okay, here the volume, and let's just say this is half the volume, one half the volume, one half of V. This pressure will be double. This will be P and this will be 2P. They're inversely related. So we could say there's no symbol for inversely related, so we say the pressure is proportional to 1 over V. That's the proportionality symbol. I didn't do that very good. It's like this. 1 over V. That's another way of saying they're inversely proportional. If I half the volume, I double the pressure. And they're directly, and that is half double. Okay? That's why they're on the same side of the equation. So if you think of it like this, PV equals a constant. If I increase my pressure, my volume has to decrease. They're on the same side of the equation. So now when you look at this, if I increase the number of particles of gas, N, the pressure must increase, because pressure is the collisions with the wall. That's what pressure is. That's what gives the balloon its pressure. So we say that pressure is directly proportional to the number of moles and also temperature. If I add a flame here, right, the pressure increases because the gas molecules have more energy, more collisions. So they have more collisions with the walls, and they have more energetic collisions, which increases the pressure. So pressure is directly proportional to both moles and temperature. That's why they're on opposite sides of the equation. You've just derived the equation. We can say that, pressure is inversely proportional to volume, so we put them on the same side, and those two are directly proportional to number of moles and temperature. Now, how do you get from a proportionality to an equation? Well, you simply add the non-scientific term, a fudge factor. But we're not doing anything other than a constant simply allows your units to work out. So if we know this relationship here, right, and let's say we have 1 atmosphere, right, and then I half it. I'm now at 0.5 atmospheres. And I initially had a volume of 1 liter, right? We have to realize that the pressure volume units have to work out. So if I want to calculate what my new volume is based on my new pressure, I have to be able to relate those. And that's what a constant does. It allows us to get the correct number in the right units. So if I have a given pressure, right, for a certain number of moles of gas in a certain volume, I should be able to calculate the temperature in Kelvin. And that's what R is going to allow me to do. So ultimately, understanding the relationship of P, V, R, and T allows you to derive the equation, and you get your constant that allows you to relate all of these. And that's what your books, all your textbooks do. They take you through these one at a time. Here's Boyle's Law. And Boyle's Law is the one that relates pressure and volume. And we just said they're inversely proportional. So here it is. Pressure versus 1 over V. Okay, otherwise you get something like this if you do just pressure versus volume. And ultimately, this has to be nonlinear. You can see that because we can't reach, a zero pressure, right, and an infinite volume as we go. So that's why you get this asymptotic approach to the x-axis. But you're going to look at a linear relationship. You can look at P versus 1 over V. Charles' law, save for class. Here's one, Avogadro's law. This relates numbers of moles of gas and pressure. And we see all this already. Pressure is proportional to number of moles of gas. So what we do here is instead of teaching these individually, what I'm saying is start all of your problems with this. Then what you do is you simply put everything that's constant on one side of the equation. So for Boyle's law, we're saying that the temperature is staying the same and the number of moles are staying the same. So you rearrange your equation so all the constants are on one side. In this case, they already are. There's nothing to rearrange. So basically, you say that PV equals a constant. And let's say I change my pressure. I have a new volume. So now what we say is P1V1 equals P2V2 because they both equal the same constant. They both equal nRT. You can do the same thing with Avogadro here. Only difference here now is I'm going to move n over here to get P1 over N1 equals a constant or equals P2 over, I might have said N. It is N, I'm sorry, I might have said V. P2 over T2. So you start by just writing PV equals nRT, read the word problem, and arrange everything that's constant on the same side of the equation, and then simply use ones and twos to relate those. So we'll do this in class. Now, there are a couple of reactions in which can't be derived from the ideal gas equation. But here's the combined gas law. So ultimately, we can write any gas law we want from this. Some of them don't have names. You can look at any relationship. We can look at, this one is PVT. I can look at PV and N. Or I can look at VN and T. Right? You can do anything you want. Some of them have names because the scientists that worked on them. And this was simply combining these two laws to give you this combined law. So there's no different, though. In this case, the number of moles of gas is constant. So you bring the T over here, and you wind up with PV over T equals a constant. Or P1V1 over T1 equals P2V2 over T2. So, the ideal gas constant does depend on units. Okay? And pressure units need to be in atmospheres. I mentioned up here, I had said here, I didn't go into it, but units, there's lots of different units for pressure your book talks about. Okay? You don't have to memorize anything. I'll give you the conversion factors, but you got to make sure your units are in atmospheres. Actually, you should know this right here. But everything's open book, open note. That's the one I really want people to be able to recognize. Okay, so that's the units. Volume's got to be in liters, pressure in atmospheres, and temperature in Kelvin, and of course, N is moles. And then that's the value of R. We'll see another value of R in Gen Chem 2, where the units are different. And this is not only used for gases, okay? It's a universal gas constant, but it actually appears in some other places too. There's also standard temperature and pressure, something you need to be familiar with. And we'll talk about this more in class, but it's standard temperature pressure, which means 0 degrees C, 1 atmosphere, or 273.15 Kelvin in 1 atmosphere. The volume the gas will occupy is 22.4 liters. Okay? That is the same no matter what the gas is. That's the beauty of ideal gases. So if it's methane or oxygen at standard temperature and pressure, they'll both occupy 22.4 liters. Now, one of the last things I'm going to do here is talk about density of gases. Now, when you think about density, you think about the amount of material, right, per unit volume. So when you think about that from PV equals nRT here, you can actually think about, okay, well, the only thing I have in terms of amount of material is N. So if I'm really interested in density, let's just rearrange this to get N over V. So I'll have N over V, if I bring this over here, equals P over RT. That's effectively your density, right? N is numbers of moles, right? So what we realize, and I'll do this in class, is that can be substituted by the mass divided by the molar mass. Because mass divided by the molar mass is basically grams divided by grams per mole. And grams divided by grams per mole is moles. So if I can now take the mass divided by the molar mass and rewrite this, I can have mass over molar mass volume equals P over RT. Rearrange that to get mass over volume, which is density, is PM over RT. So if you have the density, you can get the molar mass of the gas. If you have the molar mass, you can calculate the density. And the last couple things here, this video is running a little long. This I'm going to save for lecture, but basically when we have a gas produced, if we know the pressure and temperature, then we can use stoichiometry to actually, figure out, using the ideal gas equation, how many moles are produced or something like that. So this is kind of useful. You're going to have to apply stoichiometry, chapter 7, basically. So the quantity of the gas can be determined from the ideal gas law if we know the volume and the temperature and the pressure of that gas. And the last slide, the last part of this video here is this mixture of gases. And this is Dalton's law of partial pressure. And this is one that can't be derived from the ideal gas equation. And it just basically says, and we'll talk about this more in class, is that individual gases kind of behave independently in a mixture. And they have independent pressures. And effectively, the total pressure is just the sum of the individual pressures. And those individual pressures are going to be directly related to the amount of that gas in there. So, and we'll define that in terms of mole fraction, which we can relate to also percentages. Okay, so that's Dalton's law of partial pressure. And with that, that concludes the video for Chapter 9.